In our last problem that we just did in class, we got the temperature of 100 grams of ice up to negative 40 degrees Celsius. And in this video, what we're essentially going to do is set up a problem that we're going to do the calculations for live in class momentarily. But it's a problem big enough that it deserves its own video in addition to the live calculations. It's such an in depth problem. And here's the gist of the problem: we're at negative 40 degrees Celsius right now with some ice. And what we're going to be asked to do is heat that ice all the way until it reaches 130 degrees Celsius. And when we do that, we'll still have 100 grams, but it won't be ice anymore. It won't be liquid water. By the time we get to 130 degrees Celsius, it's going to be water vapor, water in the gas phase. And so you might think, okay, I know how to do this. Q equals MC delta T, and it's good enough. But here's the problem, several problems. Number one, you'll notice over here on the left that every phase of water has its own specific heat. And notice that the specific heat of ice and the specific heat of water in the gas phase are actually really similar to one another. I've never actually found a great explanation for that, but those are the values. And then liquid water has its well-known high specific heat. Additionally, as we heat the ice from negative 40 and we get up to this temperature here, which you see on the y-axis, 0 degrees Celsius, the ice melts at that temperature. And once it all melts, it becomes a liquid, and we can start heating it up again and eventually get up to 100 degrees Celsius, where it's going to vaporize, where we're going to boil it. And so we've got to go through two phase changes along this path. Instead of having one big problem, the truth is we end up with a series of problems. We could break this down into 5 different problems, kind of the odds and the evens, if you will, because if you look at the sections 1, 3, and 5, here we have ice, here we have liquid water, and here we have water in the gas phase. And what they all have in common is temperature change. You're heating up that substance, and as you heat it up, the temperature changes. So for the odd problems, 1, 3, and 5, we actually can use Q equals MC delta T. Now, there are going to be some slight differences for each and some similarities as well. M will be the same for all of them. We have 100 grams of ice, but the specific heat, as we just noted, changes. So we got to look at what phase it's in order to pick the correct specific heat. And the change in temperatures, we've also got to be careful on. For ice, section number 1, we're really just heating from negative 40 up to the melting point, which is at 0 degrees Celsius. Then for liquid water, which is the third section, we're going from 0 degrees Celsius up to 100 degrees Celsius. And then for finally the section where water is in the gas phase, we're going from 100 degrees Celsius up to 130. Now, it'd be nice if that was it. And we just had 3 Q equals MC delta T problems. We could do that. And that's going to get us most of the way there. But what you'll notice is that there's also energy needed at the melting point when it melts, and at the point where we vaporize it, the boiling point. So in those two sections, we've got a different kind of calculation. The main reason is the temperature isn't changing. You can see that we have right here little plateaus. Let me shade them in. So we've got a plateau right there, and we have another bigger plateau right there at the boiling point. And so the question becomes, what kind of calculation do we do? Well, we don't want to use Q equals MC delta T, because delta T will no longer be changing. The temperature's not changing, which begs a couple of questions. What's actually happening at the melting point? What's actually happening at the boiling point? We're still putting energy into the system, but the temperature's not rising, which means something in terms of the molecules. Think about it this way. When you increase temperature, the molecules start moving faster. So what we're saying is, at the melting point and at the boiling point, it's not that the molecules stop moving, they just don't get any faster. Well, all the energy that we're putting in those two um, locations on this curve, those locations are. Let me get my language together. Sorry. In those two locations on the curve, all of the energy that we're putting in is going in to do one of two things. At the melting point, I would say the best way to think of it is that we are loosening hydrogen bonds. And that takes some energy. That energy is actually known as the heat of fusion. And you can find that right over here, heat of fusion. That's the amount of energy needed to loosen up those hydrogen bonds to turn the ice into a liquid. On the other hand, when you look at the boiling point at 100 degrees Celsius, now we've got to go from liquid water to water in the gas phase. Here we're going to break hydrogen bonds. Well, how do we actually calculate those values? Well, for boiling water, there's something called heat of vaporization. That's the energy needed to break those hydrogen bonds. And I want you to look specifically here at the units, kilojoules per mole. Okay. Well, we would like energy units. Heat energy is in joules or in kilojoules. So in this case, what we're going to end up doing for both of these calculations is actually very similar. We're going to do what's called a Q equals N times delta H. And we'll just use different varieties or different versions of that depending on if we're melting or if we're boiling. So what is N? N we know from last term. This is moles. And right now we know that we have 100 grams. So what we've got to do is change that 100 grams into moles and multiply it by our delta H values to turn it into a heat value in kilojoules. And then finally, at the end of the process, we'll take all 5 sections and we'll add them together, and that will give us the total heat energy needed to change the temperature of some ice at negative 40 degrees Celsius to water vapor at 130 degrees Celsius. But we haven't even done the calculations yet. That's why we're coming back live, and we'll do those calculations together.